Hi everyone, we're going to prove statements using mathematical induction. We have a basic statement here, and on a few of these videos I'm going to try to dissect this a little bit before we prove this. You should have already finished arithmetic sequences before you start this. So we know in arithmetic sequences there's a common difference. In this case, my common difference is 2. And this would be your first term, your second term, your third term, and your nth term. And this is your sum. So basically this is the layout of it. Remember, if you were to try to find the nth term of this, say we had these three numbers, use this formula. Okay, so basically, if we want to find the sum, go a sub n equals 1 plus n minus 1 times 2. So a sub n equals 1 plus 2n minus 2. So a sub n equals 2n minus 1. So there it is. And then the sum, remember the sum formula for arithmetic sequences is n over 2 times a sub 1 plus a sub n. So it's just n over 2, and your 1, your first term is 1, and then your last term, or your nth term, is 2n minus 1. When you clean that up, you get n over 2 times 2n. The 2's cancel, and that gives you n squared. So this is where this is coming from, and I just want to state that before we get started. The other thing you need to know is what all this means. So, for example, if n equals 1, and I plug in 1 in here, that means when I take 1 squared, that should be the sum of my first term. So my first term is just 1. So let's plug in 2. If you plug in 2, 2 squared equals 4. So basically, that means the first two terms sum. So 1 plus 3 equals 4. And so I can tell you what the third term should be. The third term should be 1 plus 3 plus 5, and that equals 9. And so the third term, the sum of the first three terms is 9. So this is what all this means. Okay? Now we're going to go ahead and set to prove this. And what we want to do is proving this for all natural numbers. And what we want to do is also show the statement is true for natural numbers, just means the positive integers. So basically, I'm going to write this equation down again on the next slide. So we have 1 plus 3, which is your odd numbers, plus dot dot dot, 2n minus 1 equals n squared. Another thing before we get started, all arithmetic sequences are linear. So do you see the common difference here is 2, right? Well, that's the slope of this linear line here. So this should always match. Your common difference should match what the slope is. This is a linear term. All right, so just wanted to go over that. All right. Let's talk about our conditions that we have to do to prove this. So condition 1, that it holds for n. Well, we already did that. So basically, we're going to check for n equals 1. If n equals 1, it should equal my first term, which is 1. So I put a 1 squared equals 1. So condition 1 holds. So you're just checking for the first term. Now, before we check for the second and the third, and then we could do the fourth. We don't want to have to keep doing that. So our condition 2 basically states that if it holds for some natural number k, so for some k, okay, then it's true for the next natural number. And the next natural number is k plus 1. So if it holds for 1, then it holds for the next number. So the next number would be 1 plus 3 is what? 4. So that's what we're going to do, and we're going to set it up that way. And you have to follow the steps. So the first step is we're going to assume that it is true for some number k, because we already checked it here for n. So we're going to write the k, dot, 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 plus 2k minus 1 equals k squared. So everywhere there was an n, I put k. Now we want to see if it, and it should be, it's also true for the next natural number, k plus 1. So what you do is we're going to copy this whole thing down, copy it down, 1 plus 3 plus 5 plus dot, 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 plus 2k minus 1. So we want to know what is the next term. Okay? So what would be the next term? So what's the next term that comes after 2k minus 1? So basically to find that, what you could do is take 2, instead of k, we're going to put k plus 1 minus 1. So for the k, we substituted k plus 1. This gives you 2k plus 2 minus 1, which gives you 2k plus 1. So my next term is 2k plus 1. Now, the next term, the sum then has to include the k plus 1. So this is going to be k plus 1 squared. Alright? Now that we have this, what we're going to do is to simplify and solve. The reason we wrote this down here, so this part here, we know this equals k squared. So here it is. This part here equals k squared. So I'm just going to put the sum here of that and then add my next term. And it should equal this. So if I factor this or put it together, we get k plus 1 squared equals k plus 1 squared. Or what you could have done is taken this and FOILed it out and got k squared plus 2k plus 1. Either way, both of these would be right. So we have proven it, and we have proven that which should be proven. Alright. I also wanted to talk real quick, because the next videos we're going to go a little faster. When we did this little bit right in here, you can do it that way, but also know that this is linear. The common difference is 2. So remember when I talked about this is the slope? All we had to do was add the 2 to the y-intercept here. Negative 1 plus 2 is 1. My students tend to have problems with that. So if you don't want to do it this way, especially on these linear ones, the arithmetic, these are arithmetic. Arithmetic sequences are linear. Okay. Then you can just go ahead and add the 2, and we get the next term here. Okay, thank you and have a nice day. Bye-bye.